Well, hello there. Here are three examples that correspond to um, section or lesson 12.A and 12.B in the Hawk software. Counting techniques. Um, and I've got actually another set of examples after this as well that are posted. This is counting problems 1, and there will also be counting problems 2. Um, but counting problems 1 here, this is the first problem. Let's take a look at it. So we want to create a password with 4 letters followed by 3 even digits. And the even digits are between 0 and 9 inclusively. If the characters and digits cannot be used more than once, how many choices do you have for your password? Okay, so basically we want to create um, a 7 character password here. So you could think of this as maybe your ATM password or something like that. Uh, and we're asking the question, if this is our restriction that the first 4 blanks here are filled by letters and the last 3 are filled by even digits, how many possible choices do we have for our password? And so this is a kind of question that's actually of interest to the banking industry or anybody that has passwords and has to um, have passwords in store for their customers to use their services. But I'm going to appeal to the counting rule, the fundamental rule of counting, as it's called in your textbook. And basically, it says that if I have a task that I want to complete in K steps, and the first step can be done in N1 ways, the second step can be done in N2 ways, the third step can be done in N3 ways, and so forth, all the way up to the kth step can be done in N sub k ways. Then the product of all these number of ways is the number of ways the entire task can be completed. Okay? So now I want to apply this to this problem. My task here is I've got a 7 character or a 7 blank um, password that I'm creating. And this character or this blank here, how many ways can that be done? How many ways can this be done? And so forth. And if I figure out the number of ways of each of these, take the product, then I get the total number of choices I have for a password. Okay. Um, the, the first blank must be a letter. Okay. How many letters are there? Well, there's 26 letters. So there's 26 ways for this step to be done. The second character must also be a letter, but there's only 25 ways that it can be done because the characters cannot repeat. They cannot be used more than once. The third step here is to have another letter. There's 24 ways for that to be done. And the fourth step, there's now 23 ways because in these first 3 steps I've already used 3 letters, so there's only 23 ways left over to complete this step of the task. Now, the remaining 3 um, characters here must be even digits. So if I think about the even digits that I have, if it's between 0 and 9 inclusively, I've got 0, 2, 4, 6, and 8. Okay? And so if I think about this first even digit, there's 5 ways that I can have an even digit here. And now there's 4 ways I can have an even digit here, again because digits as well cannot be repeated. And then lastly, there's 3 ways that I can have an even digit here, right? Because starting off I had 5 total even digits, 4 because 1 was used for this character and 3 because 2 are used for this character and this character. So if you take the product of all of these numbers here, it turns out, I'm going to write it down here, you get 21,528,000 choices. So there you go. You've got plenty of choices for password. That is, unless some of the choices have already been picked up. Number 1 there. Number 2 is just kind of a mechanical calculation of permutations and combinations. So first I want to evaluate 3 permute 2. And if I think in general, the formula is n permute k or n permute r. I'm not sure what expression you've seen, but that's defined as n factorial divided by n minus k factorial. Okay? So when I look at 3 permute 2, that is 3 factorial over 3 minus 2 factorial. Here 3 is my n and 2 is my k. So in the numerator, I've got 3 times 2 times 1. In the denominator, I've got 1 factorial, which is really just 1. So I've got 6 permutations here. Now, 3 choose 2, or this is a number of combinations if I take 2 objects out of a set of 3 without replacement. And the formula to compute the number of combinations is n ck in general, and that's n factorial over k factorial times n minus k quantity factorial. And if you notice, this formula, the combination formula, is simply the number of permutations divided by k factorial. And the reason it does this, we'll look at an example in a little bit, but this divided by the k factorial accounts for the redundancies. If you recall, the number of permutations is the number of ordered arrangements of objects, and the number of combinations is the number of unordered arrangements. And so when you divide by k factorial, you're undoing the counting of the ordered arrangements from the permutation formula. Okay, oh, let me scratch that out here. So I want 3 choose 2, which would be 3 factorial over 2 factorial times 3 minus 2 factorial. And in the numerator, I have 3 times 2 times 1. In the denominator, I've got 2 times 1 there. Then that's 1 times 1 factorial, which is just 1. So I've got 6 over 2, or 3 combinations here. Counted 3 combinations. Now, let me give you some insight into how this might play out in a particular example. Suppose I have a set of 3 objects that are distinct, A, B, and C. Okay, and I'm going to draw 2 objects out of here without replacement. Okay, and I ask myself the question, what are the permutations, what are the combinations, and how many are there of each? Well, okay, so the permutations are the ordered arrangements. All right, so if I'm drawing 2 out of here without replacement, I would have A, B, that would be 1 permutation, or I could have BA, that would be a different permutation because order matters. I could also have AC or CA, now I've got 4 permutations, or lastly I can have BC or CB, and all these would be the 6. These would be the 6 permutations here. Okay, now when I think about the combinations, the formula said that there's 3 combinations if there's 6 permutations. Well, what are the combinations? Well, this is a combination. This is 1 combination. I'm not interested in whether A becomes before B or B before A. This is still the same combination. This is also a combination. This is also a combination. So there's 1, 2, 3 total combinations. And I'm not interested in the order of these letters and the combinations there. Okay. Third example. Applying one of the formulas that we just looked at, playing cards. So suppose 2 cards are drawn from a standard deck of 52 playing cards. How many different 2-card hands are possible if drawing is done without replacement? So I've got 52 playing cards. It's almost like I've got a set here. You can think of it as a set. I could have the Ace of Hearts all the way down to the 1 of Hearts, to the Ace of Clubs, down to the 1 of Clubs, the Ace of Diamonds, down to the 1 of Diamonds, to the Ace of Spades, all the way down to the 1 of Spades. A problem here is that it's been a while since I played cards, so y'all can see that. There's no 1 of Hearts. There's a 2 of Hearts. Sorry about that. There's a 2 of Clubs. There's a 2 of Diamonds, and there's a 2 of Spades. Okay. So here I have a set of distinct objects, and I'm drawing 2 cards from this set without replacement, okay, to give me a 2-card hand. And how many different 2-card hands are possible? Well, this is essentially asking what are the number of combinations of drawing 2 cards from this set of 52 playing cards here. And so I'm actually looking at 52 choose 2, which is 52 factorial, over 52 minus 2. Let me back up here. It'd actually be 2 factorial times 52 minus 2 quantity factorial. So on the top I've got 52 factorial, on the bottom I've got 2 factorial, and then here I've got 50 factorial. Notice 52 factorial can be written as 52 times 51 times 50 factorial over 2 factorial times 50 factorial. Those cancel out there. And if you take the product, you get 52 times 51 over 2. And I believe it turns out I worked this out before. That's 1326. I hope this was helpful.